Hi everyone, it's Mr. H here. This video is all about an exponential population model. We're going to look at this question in front of us, including using logarithms to solve the answer for part B. This question says the population of tigers in Africa has an exponential rate of decay of 5% every year. Notice it's a rate of decay. We'll come back to that in a moment. If the tiger population in Africa was 25,000 in 2019, how many tigers will there be in Africa in 2040? And then, in what year will the tiger population become half of what it started at in 2019? So the first thing to keep in mind here is the general equation for exponential growth or decay. It's the population after some time is equal to a times b to the power of t. Now, a is the starting population or the starting value. That's pretty straightforward here. It's going to be 25,000, which we'll sub in here in a moment. B is a little more tricky, and what we have to do with this is we have to recognize that this is the exponential growth or decay factor. It's essentially what I'm multiplying by each year to get the number I have the next year. So for an exponential growth, what I'm going to do is it's going to be 1, b is equal to 1, plus the growth rate. Now that growth rate has to be listed as a decimal. If it's not as a decimal, then it's not going to be correct. So for example, if you had a 5% growth rate, you list it as 0.05. If it's decay, we're going to write it as b equals 1 minus the decay rate. Now in this case, the decay rate is what we have because it's becoming less every year. And so we write that also as a decimal. So in this case, what we're going to get is 1 minus 0.05, which is going to give us 0.95 in our specific case. So the population after some time is equal to 25,000. That's our starting value, 25,000. And then we're going to substitute in 0.95 for b, as I already mentioned, because of that decay rate of 5%. 1 minus 0.05. So we subtract that, and we get 95%. That's what that means. It's really, I'm going to have 95% each year of the population I had the previous year. So 0.95 to the power of t. Where t, and we have to be specific here, it's the number of years, sometimes with bacteria or things you might have number of minutes or hours, but here's the number of years, and specifically since 2019, because that's where we're starting this equation off at. So we have to be very specific with how we define our t value. And so our p is our population of tigers after t years since 2019. So the first question is, how many tigers will there be in Africa in 2040? So now that we set up our equation, we can actually solve that. We take the 2040, we subtract the starting year, we get 21 years, and all we have to do is substitute that into the equation. Really, really simple substitution. You can type that in your calculator. You go 0.95 to the power of 21. Be careful that you don't multiply the 0.95 times 25,000 first, because if you did and you got an answer for that and then put it to the power of 21, it would be a lot bigger number. So just the 0.95 to the power of 21 and multiply that by 25,000. We get 8,514 tigers. We round that number, and we can't have part of a tiger. So there's going to be 8,514 tigers in Africa in 2040, according to this model. This isn't actually true, but this is a model that someone might have. So now it says, in what year will the tiger population become half of what it started at in 2019? Well, half of what it started at is 25,000 divided by 2, which is 12,500. And so we're going to go back to our equation that we had. Population after some time is 25,000 times 0.95 to the power of t. In this case, we don't know what t is, but we do know what that p of t is, that population value is. It's 12,500. So I'm replacing the p of t with 12,500, and I'm going to try to rearrange the equation to solve for t. Now, the first thing we have to do if we're trying to rearrange this equation is we have to multiply or divide first. We want to deal with the exponent last. So we're going to divide here to cancel out the 25,000 from the right side, and I get 0.5 or 1/2 on the left side. And so 0.5 is equal to 0.95 to the power of t. And here's where we can use logs. Logarithms are really helpful because when we take the logarithm of something, what it does is it takes the exponent on the one number and it brings it out in front of the log. And so what we're going to do is we're going to write this as log 0.5 equals, we can write this as t times log of 0.95. Now we can divide by everything except the t on the right side, and I get that canceling out the log of 0.95. Now on the left side, I get log of 0.5 over log of 0.95. Don't cancel out the logs. They have to operate on the number that follows. And if I do that properly, I get 13.51 years. Now, Remember, it's asking for what year the tiger population will become half of what it started in. I'm going to assume that the 2019 population is right at the beginning of the year. So 13.51 years later, after 2019, is 2032, and then 0.51 of that year. So that would be the year 2032. If you want to see more about the basics of growth and decay, check out the video on the left. For more examples of exponential growth and decay in detail, check out the video on the right. Thanks so much for watching. I hope that was helpful.